buenas noches. That's like more or less all Spanish I know, though I do know one more sentence, which for me as a German is basically how I live. It's ¿Dónde está mi cerveza? So yeah, thanks all for coming. Thanks for the invitation. I will have to do this in English. If I'm too fast or you don't understand a thing, please raise your hand and ask. If you have any other questions in between, I also answer them. So, who am I? I'm Jan-Erik. I'm currently traveling a bit in South America. I'm employed as a software developer. I was a student before, but I've recently finished studying. So this is basically my long vacation after university. I'm also a Mozilla tech speaker. That's why I wear some Mozilla swag. And the selfie with the crowd is one of the things we tech speakers do. So I'm also here in my role as a tech speaker today because I'm going to talk about Rust, which is a technology funded, sponsored by Mozilla. And I'm a Rustasian. That's what we Rust people call ourselves. And we have this little Paris crab. That's our logo. Besides writing software or studying how to write software, I also organize meetups and conferences. I was part of the organizer team for the very first two European Rust conferences, the Rust Fests in Berlin and in Kiev, last year and this year. And just last weekend, the third iteration in Zurich happened. So if you, after this talk, want to hear more about Rust, take a look at Rust Fest. We have all talks recorded. It's a pretty good way to get started and to get the feeling about Rust. And if you should you be ever in Europe, let me know. Come to Rust Fest or to a Rust meetup near you. So I'm going to talk about Rust. But Rust the programming language, of course. But we first I need to get a bit of feeling about this crowd. So raise your hands if the question applies. Who's the developer? Okay. Who's not a developer but related to developing, project management, documentation, or something else? Okay. Now I want to know a bit about the languages and the way they work. So who's a backend developer? Who does front end? And who calls themselves a full stack dev? Okay. Java developers? Okay. C? That's good. Python or Ruby or similar things? Some as well.
No, please.
Did I miss anything?
Yes.
Anything exotic?
JavaScript.
Okay. Anything else?
Go.
Go. Yeah.
Go.
Okay. Some exotic ones. That's good. Okay, so a really diverse crowd. That's good. Anyone already writing Rust?
Servo.
Writing Rust for a living or just for fun?
For fun.
Okay, perfect. We get you there. Sometime there will be more Rust jobs. So, what is this Rust? I know there were already talks here about Rust, and it turns out I wasn't even mentioned in these talks. So yeah, basically I've been here before. So today I want to talk about...
So wait, if I give a talk at Nardoz and I mention someone's street, they eventually will come?
You can try.
All right.
It often works, or you just invite them. So yeah, it worked for me. So back then I tweeted Rust made me a better C programmer, and that ended up in another talk about Rust. And today I want to show you how Rust can make you a better programmer in total. Show you a few of the core features that Rust gives you. And at the end I will also go a bit into a very small project I hacked last night, so you actually see some code. So this is Rust. You probably can't read it in the last row, but it's actually just a very simple calculator program. It was once the main example on the website, and it was also the example I used in my very first Rust talk, which was like over 3 years ago. Rust advertises itself with the following sentence on the website. It says, Rust is a systems programming language that runs blazingly fast, prevents segfaults, and guarantees thread safety. That's quite a lot in just one sentence. So let's pick out 3 things. Runs blazingly fast, prevents segfaults, and provides thread safety. These are mainly the core things that Rust wants to provide you to give you a development environment that allows you to write applications at the same speed as C, but with the same guarantees that more high-level language like Ruby or Python would give you, but it does not crash. And on top of that, it will also help you to make use of all the cores that are in your laptop, your server, or even on your phone. It does that through a couple of core features that are built into the language and the compiler, which I will talk to you about. But first, let's do a bit about the history, or historia. Good as the Spanish. So, Rust as a language was started in 2010 by Graham Hoare. Back then, he was an engineer at Mozilla, but he started this in his own free time. Even before that, he always experimented around with writing his own language, trying new features out, trying to apply the current computer science papers that were looking into how to develop programming languages. And at some point he sat down and said, I need a programming language that gets rid of a whole class of bugs that we still see again and again, especially in programs like C, where we have the same bugs over and over and over again. So he started to write this language, and at some point Mozilla picked it up and said, hey, that's a pretty good idea, because we have this huge browser here that's like 10 million lines of C++, and it turns out it crashes far too often. And it always crashes for the same reasons. And crashes are not the biggest problem, but often these crashes can actually be exploited, making users vulnerable. So we need something that allows us to take this project and bring it to the 21st century and make it actually safe to use. So they sponsored him to work full-time on that, and they hired more people to work full-time on Rust. And for a couple of years, they just iterated on the language, on the features that got into the language, and what this language should actually be. If you would have looked at Rust in 2012 or 2014, you would see very much what you have in Go today. Back then, the languages were quite similar and focused on a very similar developer environment. But this all changed in the course of 2014 and 2015 when they decided, okay, at some point there needs to be a 1.0 release of this language, otherwise no one's ever going to use it and we can't use it ourselves if it's not stable. So back then they removed most of the features they added over the year and focused on a very specific core feature set. So by now Rust is not at all similar to Go anymore. So, as I said, in May 2015, they released the 1.0 version, marking it stable, which means that the compiler was stable, the standard library, as it existed then, was stable, and they made guarantees that every version coming forward will be compatible. So the code you wrote on 1.0 should still work today, which for, I think, 95 to 96% is true. The other 4 to 5% are basically bugs that are already in a language, and all bug fixes are not considered breaking. So today we are at version 1.20, with 1.21 coming out next week. So there's a fast iteration cycle in Rust as well, but they still keep the promise of keeping your code stable and working with every new version. It's still sponsored by Mozilla. All the team members of the core team are full-time engineers at Mozilla. There are a lot of other people involved. The core team, while working full-time on it, does not have the full decision power over this language. This language is completely developed in the open. So the community gets to decide what lands in the language and when it gets pushed out. So, why would you take Rust? As mentioned before, it provides memory safety, which is like one of the big classes of bugs that we still face today. Consider buffer overflows, or things like Heartbleed that accessed memory that it wasn't allowed to access and exposed information that the server had that it should never have passed down to any arbitrary user. You get this for mostly free in all higher level languages like Ruby or Python, because the abstraction between the actual memory and the objects that you work with is so large. Rust also wants to provide what's called zero-cost abstractions. It wants to give you a language that allows you to write quite high-level code, but compile down to what your computer would actually execute and making really fast. And everything that you don't use will not be there in the program after all. So it's very close to C, but with much better ways to abstract your code. And what Rust also wants to provide as an FFI interoperability with C. Mozilla, from the start, decided that they want to merge some of these Rust projects into their Firefox browser, but Firefox is written in C++. And you can't throw away like 10 million lines of code and hope to get a new project going and deploy it to millions of users. So what they need is a way to iteratively change code in Firefox, replace it by safer Rust code, and still provide a fully working browser. So this is achieved by a very small FFI layer that Rust uses to call into C or to get called from C.
Sorry,
sure.
C or C++?
At this point, it's C because we are relying, or Rust relies on the API that is provided by C. And as there's no stable API for C++ at all, there's just no way to properly support that. But for all C++ projects, you would need to invest a bit of time to provide the C abstraction layer that then gets called from Rust or the other way around. So it's possible to even interact with C++ with some more code. And Rust wants to be low level where necessary. It wants to fit in the same niche that C has. It should work on all embedded devices. It should compile down to native code on your machine. So it needs to provide this low level access to memory, to devices, and to other features. Or as a friend of mine said, well, Rust exists to write tools that already exist elsewhere. Rust is not necessarily the language that will only be used for just the new projects, but it's also very easy to integrate it into existing projects as the Firefox browser, but also others. But as newcomers discover the language, they often just pick some existing tool that's already out there and just try to write that in Rust to get a feeling of the language. So by now we have like half of the Linux user space tools rewritten in Rust just because someone thought that it would be good to do that. So where is Rust used today? If you take a look at the website, you see the list Rust Friends, which is basically a list of companies that use Rust in production already. There are some big names on there, such as Dropbox, which wrote large parts of the backend in Rust. There's also smaller startups like OneAim and AppSignal that have very specific use cases for Rust, where they would otherwise have to use C or C++. But because Rust is on the same level, they decided to use Rust and go get the memory safety and so on for free. One production user I'm very proud of, because I was involved in this project, is the German theater in Dortmund, near my hometown, where my employer basically allowed me to write a very small tool in Rust, which is now used in an opera play to coordinate MIDI music with the OC protocol, which controls the light and movement on the stage. So this is running Rust code basically in production in an actual opera production. It's Einstein on the Beach. Maybe you have heard of the opera. It was quite popular. I already mentioned this a bit. How Rust? Rust is developed in the open. It's fully open source. It's available on GitHub in the Rust Lang organization. There's Rust C, which is the main compiler, which is also defining the language. And there are a lot of accompanying tools and libraries that are also handled under this organization. If you take a look at there, you will also see that there is not only the small core team developing Rust, but over 1,000 or 2,000 committers actually contributing code to Rust itself. Rust uses a process called RFCs for all major changes in the library. You maybe already heard about RFCs. For example, all the internet standards are also in what's called RFCs, request for comments, defined. This is basically a way for everyone in the community to propose a change, but it also needs to list all the advantages of the changes, but also need to look at the drawbacks of certain changes, and is then open for the community to discuss. And this process evolved over the years. So by now you tend to have RFCs that are just a page long, but get like 100 or 200 comments in like a week. So it's time-consuming to follow this. But whenever you take a look at the language and you see a feature, you most definitely can find an RFC that describes this feature. Then you can take a look, why was it added that way, or why was another approach not taken. And as I said before, this is open to the whole community. The core team members or team members of other teams have the final say about whether this gets approved or not. But it's to be discussed by the whole community. And the core team actually listens to that. And quite a few RFCs that were proposed by the core team were actually rejected by the community because in a larger discussion it turned out that the feature wasn't a good idea at all. Rust also follows a pattern of very frequent and constant releases. There are basically 3 trains that Rust writes, very similar to both Firefox and Chrome, which is we have a stable release that's happening every 6 weeks. We have a beta release that's also, of course, happening every 6 weeks, which is basically the next stable. And we have nightly builds that are hopefully more or less built nightly on the build machines and that you can use. There are few things that are noticeable about this, and this is certain features are actually hidden behind certain flags in the compiler, and these flags can only be accessed on the nightly compiler. So whenever there are new changes that change a certain pattern or add a new library to the standard library, you can try them out on nightly, but you need to pass certain flags, and you need to basically wait 12 weeks to actually get them in stable. So, enough about the history and the what and where and when. Let's take a look at a few of the core concepts that define Rust as a language and how it achieved that. So the core concept I picked is the ownership and borrowing system, which is like the core feature of Rust, which is in nearly no other language like this. Then I take a look at explicitness, where it is okay. Sometimes we drop this explicitness in Rust. Then I take a look at the compiler support, and lastly at how Rust wants to provide better tooling to the developer. So, the ownership and borrowing system. Just from the names, you might already get an idea what this means. Ownership means that every single piece of data in your code always has exactly one owner. And this owner is also responsible for handling the resources. Consider a memory buffer. At some point it needs to be allocated, and when it's not used anymore, it needs to be deallocated. If you forget the last step, you get a memory leak, which is not that critical security-wise, but if you do that much too often, your users will complain that there's no more RAM left for other applications. If you do that in C, you always have like the malloc and free function, and you always need to remember to call them at the right time. But in C, for example, if you do double free, you won't often notice, or if you do a free and use the memory afterwards, sometimes it works, sometimes it does not work, but it will lead to very serious problems. In Rust, this is handled differently. There's exactly one owner, which basically comes down to it's the variable in some scope, more or less the function, And if this variable goes out of scope, the data with it goes out of scope as well. And if it was allocated from the heap, it gets deallocated. If it was the open file, it gets closed. If it was a network socket, it gets closed as well. All this is handled by the ownership. You can pass on ownership, so someone else is responsible for it. And at that point, the other person or the other point has to handle the resources. But most of this is very implicit and handled by the compiler. You can't do it wrong. Obviously, just passing data around is not always a good idea, because if you just want to modify it, you would need to copy it, modify it, and then somehow return it. So there's another concept, and that's borrowing. Borrowing basically allows you to hand out multiple pointers to the same data. But in contrast to other languages, you have explicitness between mutable and immutable data. So you can either borrow something multiple times immutable, so everyone that has a reference to this element can read it but cannot change it, or you have exactly one mutable borrowship, so the other point that got this data can now modify it and can be sure that no one else is reading it at that point. And this already catches most of the thread safety issues. You can't have a data race with this approach, because there can never be someone reading and someone else writing the same data. And this is one of the core concepts which the most people struggle with when starting with Rust. So are you ready for some code?
Yeah.
If it's too small and unreadable, I will explain what's on there, so bear with me.
Oh yes.
So I will again explain the ownership and borrowing now with code. I have a very simple function. Rust is very C-like from the syntax. So I have a function, it's named greet, and it has a parameter called name of type string. And it now wants to print this string.
Yeah.
At this point, the function greet gets ownership of the string that's actually passed to it. So at the end of this function, the string is actually deallocated, because the ownership lies in this function. When the function ends, no one else has access to it, so it can be safely deallocated. Obviously, again, you would need to copy data into it, and that's quite wasteful for a lot of approaches. So we have immutable borrowing and mutable borrowing. On the top, we have the immutable borrowing. It's basically the same function, but now instead of just taking a plain string, which would mean the ownership, we take a reference to it, which can be compared to a pointer in C or a reference in Java. But at this point, we can be sure we can't modify this value, and no one else can modify this value. There might be other points in the code that read the same variable at the same time, but it won't modify it, so we can safely read it.
Sorry, I'm doing. Maybe I skip your explanation, but in the first time you receive a copy.
No. Actually, you don't receive a copy by default. You have to be explicit about copying the data. There. So if you just pass on ownership, you will pass on the data and won't have access to the data anymore. If you want to keep the data, you need to copy the data and make an actual clone of the data. So that's very explicit there. On the borrowing side, on the other hand, you just pass a pointer or a reference to this data. So you're not copying anything, you're just creating a pointer saying, okay, the data you need to look at is somewhere else in memory. If you take a mutable reference, which is indicated by the &mut, you can be sure that no one else at the moment is reading this data. Not even the owner can read the data at this moment, because there's someone else having a mutable borrow. So at this point, we can modify the data, we can call function on it and modify it. And when this function returns, we're not deallocating anything because we don't own the data, but the data that is in memory will be modified. Everyone understood it so far? Perfect. This is now very simple. It gets more complicated in actual code, and this is actually a thing that most people struggle with. But if you compare that to C or Java, where you're just passing around data and have no idea if what you're actually doing there is safe, if you do this for a week, you come back to see your Java and you see all the problems with your code. Okay, so this is the first concept. I'm going to skip more code, but we're going to take a look at my actually implemented code afterwards. So I wanted to mention explicitness. Rust tries to be very explicit, both about the types it's using and about the code that you're writing. And even the error handling there is very explicit. Where in C, you just return a negative value whenever you can to indicate an error, and a positive integer value to return whatever success value you have. You instead use other data types in Rust. You take, for example, a result, which can have two variants. It can either be OK, which is the success value, and wraps another type, or it can be an error of some other kind. More or less, you can put in a string to show your user when there happened an error. Don't worry about the syntax right now, you don't need to understand it fully. But basically, we can define these two variants of a type. And we can then make the error handling quite explicit. So if we have a function, in this variant it's called this can fail, it takes a boolean that's named succeeds, and it returns a string, a result of either a success value of string or an error value of string. Right now that's not really usable, but it's enough to describe the concept. So we then just switch on whether or not this function should succeed, and if it should succeed, we return the OK value, otherwise we return the error. And now in the main function where we get the result back, we can't just blindly access the data, but we need to verify that we are actually dealing with the OK value or the error value. And in Rust, if you, for example, want to deal with errors in just one place, you can just return the error again from your function until somehow a higher point in your code actually treats the errors, displays it to the user, shuts down the program, or whatever is necessary to handle this error.
One thing hack.
Is it? Do you need to you explicitly define a string on the OK and error? Is that because it's defined?
Yeah. So basically, result is one of the built-in types of Rust. It's actually just this definition. It's an ism of result with two generic types: the actual success value and the error value, which is indicated by the square brackets here, angle brackets. And then you have an OK of some type T and an error of some type E. And in your code, you then actually define these generic types to be some specific type. In our case, we just picked a string for both variants for easy demonstration. So again, the error handling here is very explicit. This sometimes results in more code that you need to actually write, but it also forces you to actually write this code. I've seen dozens of different applications in C, Java, Ruby, or whatever that always only handle the success case and never handle any errors. So whenever you put something in that the function didn't expect, your whole program blow up.
The alternative, if the Go approach, Go returns a tuple.
Right. Again, Go, for example, has the thing where you return two values. The one is always indicating an error, and the other one is the actual value. But Rust Go does not force you to actually check the error. You can just drop the error and continue with whatever was returned as the success value without ever checking if there is one. In Rust, this is all very explicit. You can't access a success value that's not there.
Do functions always need to return a result? Or?
No, of course not. Like, there are functions that definitely won't need a result because they can't fail. Like if you just return always the same integer, it does not make to return a result. But a lot of the times you actually want to do this, you can either express this through a result, which is the data type in there, or you actually need to find your own data types that express better what you're actually doing. For example, there might be very different cases that your function can work. It can either return a success value, or it can return an intermediate value, or it can return an error. There are much more ways that you can express this. And it's always explicit in the type that you give.
sorry.
Sure. Let's do questions first. Yes.
So the non-constructors take ownership of the arguments?
In this case, yeah. In this case, right, it takes just the ownership.
That's by default, or you can specify?
Yeah, it does that by default. If you specify it like this, the ownership gets into the replicator. But you can also pass in references if you annotated it correctly as references. Then you can have pointers in this enums or structs pointing to some other data. And at that point, Rust will actually make sure that your code is sensible in the case that the reference that you're passing actually lives long enough. There always needs to be an owner. You can't give a reference, then drop the owner, at which point the data would be deallocated and have a reference somewhere. It just doesn't work.
Sorry. This example, which is
Yeah.
There is no type error when it's called print line.
I haven't.
If we change the error type from string to anything else.
So I didn't mention this small little detail. So println is a very special function in Rust. It's a macro. It can basically handle everything that implements a certain trait. It's similar to interfaces. So this trait defines that something can be displayed. And with this special syntax with colon, exclamation, question mark, you actually tell it, give me the debug output. Give me some representable value that I can use to debug this.
And that must be implemented for the type error.
Right.
Okay.
It needs to be implemented for the result and then for both the error case and the success case. In case of string, the displaying of the string is pretty obvious. In case of a result that has a string, you just wrap it in the variant. But of course, for your own data types, you can define this on your own and include data that you need to debug it. So in this case, it will work as long as the type that you put into the result is also debuggable or debug representable. Okay. Yes.
I don't know if you're going to see this later, but how do you ask if the result was okay or error?
Oh yeah, that's actually a good question. I do have a playground link here, so I'm gonna.
Later is okay.
So, this is the Rust playground. It's basically a website where you can write Rust. It gets sent to the server, compiled, and sent back. So we have this function here. Is this big enough? I guess. So if we run this, we will see that we get an OK success value, which is the debug representation of the result. Now, if we say like fail, please, we get the other case. There, we got an error. Now, this is only showing the data. So if we actually want to handle it, we have several different ways. There's one pretty powerful construct in Rust. It's pattern matching. And you can basically match on what's in there. And then you can say, match this, and if it's an error, I don't care about the error. Just say,
Cascade everywhere.
yeah, so.
So there is a way to not care about the error.
Well, yeah, you can, but you have to be explicit. You need to actually write the code to make it happen. So if we now do this, it will get the result back. It will match it, see that if it's an OK value, then it print the one line. Otherwise, it will just print whoops, and the error is gone. But you can, of course, replace this underscore with a variable name to actually catch this and handle the error from there onwards. This is basically it. You can also be very explicit that you just don't care. At which point you will get access to the OK value or the success value if there is not one. But if there is an error value, the running program will just abort. But it will safely abort, so it won't leak data, it won't expose any of the memory that had been used, and there will be no buffer overflow or otherwise crash that you could exploit. But again, this is very explicit. You actually need to write unwrap And the first thing I do when I get to a new Rust code base is run grep -c ungrep star and just look how many unwraps there are. Because if there are far too many, you know that someone didn't care about error handling and this should be fixed. There might be valid use cases, but I prefer to avoid unwrap at all costs. But for examples, it's often the way to go.
And
Good.
what is the best practice there? To use the pattern matching? How do you avoid your code to be full of pattern matching?
Yeah, you can. This requires, to avoid all this pattern matching, you require a bit more things to know. This is, we can, let me just call this, and we return a result of nothing or a string. And now we can do the following. We can call what this can fail, false. Got something. Okay. So what this is doing, maybe you should call that function. So I'm going to explain this in a second. So we have some special syntax to deal with this. Now, how about we? Yeah, okay. Now this works. So we have a special syntax to deal with this, and it's the question mark operator.
Question mark, what?
The question mark operator basically takes a look at the value that's in there, and if it's an OK value, it gets you back the data. And if it's an error value, it will just return from the current function, returning the error. And then you can basically bubble up the error and handle it at some data point. So you need the pattern matching only at the very end, where you actually handle the errors, and in your code you can be quite concise and handle the good case.
Is part of the result interface, the question mark? Or?
Yeah, exactly. It's part of the result interface defined for that. And in the future, you can also apply it to a few other things, but that would be much more.
What is the recommended way to handle like different types of errors? For instance, you want to distinguish between like file not found or cannot invalid access or stuff.
So you can basically in the error value you can put in whatever data type you want. So if you're writing a library, you most likely define your own error type that has all the different variants that you can have. For example, for the API handling all file operations, there are the standard errors defined, like file not found, not allowed to open this, or some other error. And these are all defined in the own error type. And when you unwrap the error, you can then match on this error, explicit error type, and handle the different cases. For example, showing different error messages, try again, or however you need to handle it. And this is also for your own use case. There are a lot of libraries that help you making this easy.
You can overload the response for a fail.
Sorry?
You can overload the response.
Well, in Rust you can't really overload, but you can basically extend more types. And through basically the trait system, you can define certain behavior.
You are using the question mark in the print line.
Oh, the question mark in the print line is just the syntax for actually printing something. This colon question mark is saying call the debug representation of that. If you know C, or I think Java is the same for the printf thing, where you use a percent sign and then some formatter, Rust decided to go more the Python way and use the brackets with some things defined in there.
It's not related with errors.
Okay, the third thing I wanted to mention is compiler support. The compiler is actually pretty good at guiding you to write correct code. For example, here I have a very, very small main function. It defines a variable meetup with the string value Nardoz, and it tries to print the meetup variable. If I try to compile it, throw that against Rust C, I will get an error which says, well, I can't find the variable you said I should use, but maybe you meant some other variable. By now this is pretty standard, even VCC or Clang for C code can do this, Java probably does this as well. But getting there and helping the user in that way is also something that Rust C is pretty good at. And it doesn't stop at just simple renames. It also catches actual bugs in your code and refuses to compile the code. Here's another thing, showing the good Rust error messages. I have a function that's called borrow same field twice, would. Basically, the function name already says what it does. It tries to mutable borrow one and the same field of some struct foo mutable twice. But as I said before, you can't have two mutable references to the same part of the code. So if you try to compile this, the compiler will say, hey, I can't do this. You have a mutable borrower at line 9, and you try to do another mutable borrower at line 10. This just doesn't work.
Well, I expected a warning, not an error. But maybe.
No, in Rust, this is an actual error, because this code can't be correct under what Rust sees as correct. Two mutable borrowers just go against the borrowership system.
Okay.
So there, Rust tries to help you or guide you to write correct code.
What about if you want to do it in a multi-thread environment? Can you?
I won't touch on this in this talk, but basically you can do this, obviously, but you can't do this with just a mutable reference. If you do that in C, I bet you your code is broken. What you need to do in C, but no one or the compiler won't tell you, is that you need to use some form of data around that to get single access, like a mutex to lock the data. In Rust, this is also possible. You just take a mutex, and the mutex then knows, okay, if I'm locked, someone else in some other thread can't access it while I'm locked. So basically sleep them. I'll do my work. When I unlock, wake the other thread, and you're done. But this is very, very explicit. You can't fuck this up, and Rust will stop you exactly from these problems.
So basically, it serializes the resources.
Sorry?
It basically serializes the resources.
More or less, but it gives you the tools to make that very explicit and will stop you from But there are ways that you don't need real serialized access. Like you can have atomics, which obviously can be modified for multiple threads. Or you can give read access to multiple threads, because there can't be any problem just reading from multiple threads. So all of this is defined in the type system, and all through this borrowership system can be achieved. And the fourth point I wanted to make is that Rust, from the get-go, started to make tooling much better than what we had before. In C, we don't have one unified package manager. In Ruby, we have two, which basically one building onto the another, because people learned that some things were broken in Ruby gems, so they built bundler on top. In Python, I don't know how many there are in current use, but far too many. In Java, there are basically Maven and I don't know what's there.
Gradle.
Yeah, Gradle. So there was the need for that in Java as well, but they still don't have like one fixed solution. In Node.js, we have NPM, which is pretty much a very high standard when it comes to package management. So Rust took a look at all of this and said, well, let's build on what's already there, and let's take the ideas and build one single tool that does that. So they hired the guy that built bundler in Ruby, because he knew what to not do in a package manager. So he wrote Cargo, which is this package manager, build system, and registry tool for Rust. This allows you to build your projects, add dependencies, release your projects to a registry so some other person can use your library. By now there are 11,600 crates online, so libraries that you can actually use. Last time I gave this similar talk, it was like 3,000 less, which was like, I think, like 4 months ago. So you can already see that it's growing by every day.
sorry, I don't understand something.
Sure.
In NPM, the Node.js world, you have a package manager and maybe a registry. Why do you need a build system?
So because Rust is a compiled language, you need some way to invoke the compiler that compiles your code, but you need to tell your compiler which dependencies to use and where to find them. And especially in the world where you also want to link to C, you also need to know where your system has the C libraries. For example, OpenSSL or ImageMagick, which are huge C libraries that are basically on every Linux system and a Unix system out there. And you don't want to rewrite all of them because that would be far too much work, but you want to use them. But you don't want to fiddle around with make files and figure out where to find these libraries on your dozen different systems. This is all the job of Cargo. Cargo is very opinionated about how it does that, and this currently is quite a struggle for a project trying to integrate it. But we're working with the huge projects from Google, from Facebook, and other open source projects that are their own build system, for example CMake, to better integrate Cargo and to make it work with the already existing thing. But basically, Cargo takes all of that from you. You specify your dependencies once, and Cargo knows where to get them, how to compile them, how to link against them, and how to update them. So if you have Cargo installed, which comes with the usual Rust release, you just have Cargo new, and you get a whole project structure, where you can define your dependencies, define your code, add more data as you need it, and build your project. And then you just call Cargo build, which takes a look at your manifest, downloads your dependencies, and just builds it. And it spits out a binary that you can then use. This also means that most of the time you don't need Cargo or the full development environment on your target machine, because you can compile your code once and just deploy the binary. Whereas for Python or Ruby, you always need to have all the gems installed on the system as well, which basically means you either completely vendor them or you have Ruby gems on your production server as well, which makes it sometimes quite difficult to maintain that in the long run. Yes?
Do the registry handle multiple architecture?
Sorry?
Do the registry handle multiple architecture?
The registry actually just hosts the source code. So it won't host the compiled binaries. So what Cargo is doing is always downloading the source code and compiling it on your machine.
Oh.
So there's no need to handle multi-architecture. But Rust-C, the compiler itself, can handle multi-architecture quite easily. You just tell it what to compile for, and then in the hope that you actually have a compiler that does that, can do that. Or the libraries, the linkers that you need. So it is possible to have a Linux machine and compile for Android or for a completely static build. It's theoretically also possible to compile for Windows or macOS, though you need more tools which are not that easily accessible. But basically the setup is already there.
Sorry, do they use LLVM underneath?
Yes, yes. They bundle their own LLVM, which basically gives us all the compiler and targets for free. And we're always trying to keep up to date with LLVM, which is not that easy, but yeah. But that also bounces to what the actual possible targets are. So right now we're missing a lot of smaller embedded boards that don't have a target in LLVM. But this will change with LLVM growing as well.
When you try the online compiler and runner, you show LLVM and ASM too.
Oh, yeah. Basically, this is all handled by Rust-C itself. Rust-C has its own copy of LLVM and knows how to invoke all of this. You don't need to think about LLVM when writing Rust code.
Right.
Just to mention a few more things that are there in the Rust ecosystem regarding tooling. There's the Rust language server, which basically tries to export information that the compiler can get from the code to be easily accessible by IDEs or code editors. There's a pretty good integration into, for example, Visual Studio Code. So it gives you all from tab completion to type information to actual error messages while you write the code. We also have Rust format. Basically, the same thing as Go format. It tries to take a code and format it in one way, which I think, regardless of the actual format that's used, is a pretty good thing. And we have Clippy, which is basically a collection of lints that are not in the compiler itself, but they sometimes catch bugs and sometimes just catch very inefficient code. They're quite easy to write. There are like 150 custom lints in there. So I highly recommend to take a look at that as well if you're writing Rust code. And this is all pretty easy installable by Cargo itself or by the Rust system that you got. Okay, that was a lot of things about Rust. Now I do have a small demo because last night I sat down and thought like I can't turn up here without any code. The problem is currently I don't have a library or a project on my own that I would use. So I just looked around what I read about in the last couple of weeks and picked a few tools and threw them together. And I had this idea of writing a small search engine index. And basically what I took is the IRC channel messages from the Rust channel of the 3 last years. Wanted to build a web front end for that and then be able to search by nick and messages. So I do have that working. I can get that up here. So I do have this project here, which is, let's see, yeah, basically it's 230 lines of code.
Okay, would you like zoom in the font size?
It's as large as I get.
Okay.
Wait. I do have. Where is it? There it is. I do have this open. This is better. So.
Right.
See. So I have this. This is basically the definition of my project. It gives it a name, gives it a version, and it lists all the dependencies I have, of which I used quite some. Basically, I have a search engine called 10TV. It's completely written in Rust. So first I had another project in mind I wanted to write. Turns out I had to link against the C library, and the C library was broken, so I threw it away. Now I'm using 10TV, the search engine written in Rust, and using Rocket, which is a web framework written in Rust, and using Rust quite heavily. I can just briefly show the code. So basically what it does,
dependencies always match by equal.
I can show. So what Cargo does, the build tool, is here you list the names of the dependencies and give it a semantic version. And what Cargo actually does is this is equal to caret. I think it would be caret. So basically every minor patch is valid, but it won't do a major version upgrade. You can be very explicit and like basically use all the semantic version ranges that you can think of, like equal, then it definitely will pick this one, but you can be free there. Like if you just write the number or the version number there that was stable when you used it, Cargo will do the right thing and at least get the next minor version.
How to resolve dependency version conflict? In NPM, Node.js, you can have two libraries that depends on two different versions of sub-libraries.
That works the same in Rust, at least for purely Rust things. It does not work if you link against system libraries for the single reason that C does not allow that. But basically Cargo tries to help you as best as possible to pick the best version number possible there, and if it's not possible to pick just one, it will pick different dependencies for different or different sub-dependencies for your dependencies. Okay, so I got this. Then I have some code. Basically what it does is I do have two modes. I can index the data that I have, which is basically just the IRC logs I collected over the last 3 years. Then it does build the index using this library, which is quite easy. Oh, I do have it disabled. We can build index. Where is it? Anyway, there it is. Okay, so basically what it does is it creates the index. I tell it to use 3 different fields. I have the time, I have the nickname and the message, and then I just pass the data using some regular expression, throw it in, and the search engine will do the right thing with it. And now if I run that, I think I can do it from here. Cargo run. No, I can't. No, okay. Anyway, that should have worked. So on my machine I have like 150 megabyte of data, which accumulates to like 2 million lines of IRC messages. I'm sure I dropped out sometime in IRC. So this takes like 10 to 12 seconds to index, and then we'll basically the index is around 20 megabyte for that, plus the data. And then I have this nice web front end, which is Rocket. And once I ignite the rocket, it will start up, launch to the moon, and give me this web server that I can then just browse. The exact code is a bit more than I would love to, but basically it just takes the query parameter that you get via GET request, throws that into the search engine, which knows how to parse the query, looks in the index, and gives you back the documents. And now if I find the browser again, we can actually launch that. So I'm gonna run this. So it launched. That's good. Let's try it again. There it is.
Awesome.
So I now have a search engine that allows me to search, for example, for Nardoz. And turns out Servo actually announced his own talk in their IRC channel back in 2015, or another talk.
Crystal language.
So that actually works.
Better than Microsoft.
Sorry?
Better than Microsoft.
Yeah, sometimes. So we can look up all the things. So this pretty much works with a couple of lines of Rust and a bit of JavaScript in the front end. And now allows me to search all the IRC logs I have.
That's good.
I do have one more thing that I wanted to show you. Because, as it turns out, who here is using Firefox on his laptop? Okay, let me just pledge something. Try it now with the beta, and in 6 weeks try the new version, because you will be amazed. Any case, if you try it right now with the current version, you will already run Rust code on your machine, because there's Rust code in Firefox by now. And this comes from what's called Servo. Servo is basically the browser engine that Mozilla decided to write when they had Rust to see if Rust actually works. So Servo is more or less just as old as the Rust language itself. And by now it's so advanced that they're picking out different libraries of this browser engine and turning it back in Firefox to make Firefox faster, more stable, less memory hungry, and will use all your cores if possible. So please, if you try Firefox Beta 57 or in a couple of weeks the stable version, you will be amazed by how fast it is. And it will even get faster with more Rust code in there. So yeah, basically this is running Servo, and the same works here. So basically it works there as well. And this is now basically running just Rust, calling my Rust server, which calls the Rust search engine, which indexes my Rust IRC channel to show me Rust messages. Woo! So much for this. Yeah, basically 250 lines of code, not even 350. 160 megabyte of input data of 3 years of idling in the Rust channel. 180 megabytes of index with the data, so just 20 megabytes of index. Last time I checked, 16 seconds for indexing, and of course a blazingly fast web frontend now. If you want to take a look, I will upload the code as soon as possible, once I removed all our shit comments. So this is the things I already mentioned I used. Tentally is a full-text search engine. If you're into search engines, the dev wrote 2 or 3 blog posts about how he developed that, which are quite interesting, and not only Rust focused. I used Rock, a web framework, a very advanced web framework. I used regex, the Rust regular expression library, which by now is one of the fastest regular expression search engines out there. And I used 30, which is the framework for serializing and deserializing. There are different implementations of that for different formats like JSON. And especially for JSON, it's one of the fastest deserialization frameworks out there, faster than implementations that have been around for years in C or Haskell. I do have more Rust if you want to learn more of it. Take a look at rustlang.org, which is the main site. If you want to have more resources, go to community.rs/resources, which is the homepage of the Rust community team, which I'm also a member of. Or go to play.rustlang.org, start writing some code, and just experiment with it. So, muchas gracias. Woo!